The title of this presentation is Bespoke Behavioral Processors. My name is Benjamin Carrion Schaefer, and I'm an assistant professor at the Department of Electrical and Computer Engineering at the University of Texas at Dallas. This work was done in collaboration with my graduate students, Rohit Srikumar and Prada Chodari. Let's look at the motivation of this work. Many emerging applications, like IoT and medical, require simple controllers that continuously execute this same application. These controllers need to be inexpensive, which implies that they have to be small as possible, and ultra low power. Now, not all the resources in a general purpose processor are always used. That means there's a large potential for simplification. For example, we can remove unused instructions. Now, at the same time, raising the level of processor design abstraction from the RT level to the behavior level has some key benefits. First, it opens the window to new optimizations, and second, it allows to fully re-optimize the processor design as opposed to pruning the logic at an already synthesized gate net list. Let's look at how we can design processors at the behavior level, means in C for high-level synthesis. If you look into this figure, the processor is completely defined in C, C++ system C. And it has two arrays, an instruction memory and a data memory array. The processor itself is basically a big switch case that has all the instructions, the processor. The processor is then synthesized using high-level synthesis into RTL, varilocal VHDL, and after logic synthesis, we obtain the gate net list. This is the hardware flow. Now, the software flow, the input is again C, but this is the application, the workload running on the processor. We use a cross compiler to create the machine code, right? And you see here you have the instruction memory that is stored into the array that the processor will then read, and the data memory. Let's look at the proposed flow. It's composed of four main phases. The first phase does some pruning of the instructions and basically deals with the software optimization, while phase 2, 3, and 4 deal with the actual pruning of the processor at the different level of VLSI design abstraction from the behavioral RTL to C. The input to the flow is the workload that will run on the processor in C, and the behavioral description of the processor. In this case, it's a scalar MIPS processor. Let's quickly review the different stages. Phase 1 deals with the reduction of the number of instructions. This is important because the less instructions our processor executes, the smaller the instruction memory becomes. And also, what we try to accomplish here is to reduce the different types of instruction being executed. Because as you can imagine, the type of instructions will affect the amount of pruning that we can achieve. And for that, this stage tries different compiler optimizations. Phase 2 does the pruning at the behavior level. So the input is the behavior description of the C processor, the MIPS processor. We profile, simulate the code, and we remove all the instructions not being executed. After this, we call the high-level synthesis tool, and our process generates synthesizable RTL code. The advantage of this flow is that the high-level synthesis tool will fully re-optimize the RTL code based on the logic on the descriptions pruned. Phase 2 does the exact same thing at the RT level. After high-level synthesis, many more operations are made visible. Think about a for loop that has been unrolled, right? So now these operations within those for loops can now be pruned. So we do the same thing, profile, simulate, prune, and after this we generate new RTL that is then synthesized to obtain a gate net list. The last phase does the same thing at the gate net list. Right? We simulate, we profile, we prune the net list, and when we remove the logic that is not being used in the simulation, and obviously we need to do some stitching together to make sure that the functionality is still correct of the gate net list. The result of the flow is the gate net list of our bespoke processor. Let's look at the experimental setup. As high-level synthesis tool, we use NEC Cyber Workbench version 6.1. The logic synthesis tool is Design Compiler from Synopsys, the RTL Simulator Mentor from ModelSim, the scalar processor used, in our case, the MIPS processor is taken from the CH-Stone benchmarks, and you see here the table different workloads that we run on the processor. One important observation is the instruction utilization. Intuitively, the less instructions a workload uses, the larger the optimization of the processor, because more instructions can be pruned away. In the paper, we actually did a more detailed analysis, creating some synthetic benchmarks and showing how the instruction utilization affects the optimization of the processor. Let's look at the experimental results. And this figure shows the area reduction, power, and delay reduction of our method compared to the state-of-the-art that does everything at the gate netlist, the gate netlist synthesized version of the processor. And we show that on average, our approach can lead to processors that are 71% smaller, consume 62.1% less power, and are 46.5% faster compared to the original general purpose processor. And compared against the state-of-the-art, we are about 9.3, 11.6, and 8.9% better in terms of area, power, and delay. Let's conclude the work. In this paper, we presented a method to simplify simple behavioral processors. We've shown that starting at the behavior level allows the processor to be re-optimized after each of the different VLSI design stages, leading to these extra benefits, right, in experimental results compared to just optimizing a processor. A general purpose processor specified in the gate netlist version shows that we can achieve around 10% better area, small area, delay, and power. This concludes this presentation. Thank you for watching, and if you have any questions, please send me an email or write your comments in the chat. Thank you.